5 minutes. So today's experiment is determination of dissolved oxygen content. But if you look at the experiment or manual, you can see my screen.
Yes, ma'am.
Okay. So তোমাদের এই যে experiment আছে, experiment 4, this is about the analysis of water. So all the properties of the water, especially the physical properties that are necessary for to make sure that this water is usable for either drinking purpose or for industrial purpose. So first thing you have done, you have seen the how to determine the hardness of the water using the EBT indicator. However, then we have some other experiments. Okay. We also have did this one, the determination of the calcium in the presence of magnesium. However, the part C, which is determination of total solid in water. This is, you can see, it's not much of a chemical procedure. It's just the procedure is given here, measure about 100 or 200 milliliters. So you have to know the known volume. Okay. However, for these experiments, one of the important thing we haven't right here is you have to also take a note about the temperature. So you dip a thermometer in the water, sample water, take the water temperature, and then you measure the volume because it's temperature and pressure dependent quantity. So measure about 100 ml sample water by means of a pipette into a previously weighted beaker. That means you take a beaker which is dry, clean and dry, and then you take its weight using a balance, and then take about 100 milliliter of sample water. Now, if the temperature is 25 degrees Celsius, 1 atmospheric pressure, the 100 milliliter of water should weigh how much? Remember the density of water? What is the density of water?
1000 kilogram per meter cube, ma'am.
Okay, or you can say 1 gram per cc or cubic centimeter, right? Because we are using milliliters, so cubic centimeter is 1 cubic centimeter is 1 milliliter. So you can see that. So theoretically, the weight of the water will be 100 gram or 100 gram per. So because you are taking 100 ml, so that should be close to 100 gram. If the temperature and pressure are 25 degree and 1 atmospheric pressure. Okay, now what you have to do, write down whatever the mass of the sample and then evaporate to dryness on the water bath. So after that, what we put those beakers in water bath that we have in chemistry department. That's like a heater thing, but you have water there, so you don't overheat the sample. So you keep the beaker in a nice stand inside this water bath and let it evaporate slowly inside that water bath. And when it's dried, then you cool the beaker, you clean it, the outside of the beaker, so that no water left over, and then let it dry inside a desiccator. Desiccator is a kind of a apparatus, glass apparatus, where we have like some chemicals like sodium sulfate or silica gel, which can absorb any remaining moisture in the air. Okay, you have seen in some electronic devices when you purchase them, inside that there are small silica bags. Have you noticed that? Or with some medication also sometimes present those things. দেখেছো ছোট ছোট প্যাকেট থাকে যার ভিতর থাকে সিলিকা জেল থাকে. Ever observed these things?
জি ম্যাম.
Okay, so these silicas are there to absorb any leftover moisture present there. ঠিক আছে, ধরো বাতাসে যে পরিমাণ ময়েশ্চার বা ইয়ে আছে সেটা জলীয় বাষ্প থেকে, ওয়াটার ভ্যাপার থেকে, these silica gels can capture them. So it makes a dry situation for the substance. So in desiccator, we also create this kind of situation. We have a lot more silica gel in there, and so we place that dried beaker inside that, let it cool, and then you actually then take the weight. Then you keep it again in the desiccator and take the weight at 10 minutes interval until a constant weight is obtained. Okay, so if it didn't get dried enough, then after 10 minutes you will see a different weight. And if it dried well, and if nothing is to dry again, then the weight will become constant. So you will get something constant weight, and at that time, that means when at least 3 measurements didn't change in their mass, in their weight, so you say it's done, and then you take the final weight minus the weight of the empty beaker. So you already know the empty beaker's weight. Empty beaker's weight was also taken in the same manner. That means you first take the empty beaker and place it in the desiccator, take the empty beaker again, like 10 minutes interval, and if you get a constant mass, you take the mass for the empty beaker in that way. And now you have put the water, dry the water, so whatever leftover, whatever the solid is, that doesn't get evaporated at 100 degrees Celsius, that will be left over inside that beaker. Okay, so that dried substance is a solid substance which was dissolved or maybe undissolved in colloidal state or whatever present in your water sample. Okay, so you can find it by subtracting that final weight with the solid sample and the beaker minus the weight of the beaker. So this is nothing, no chemistry there, so we are not doing here. Even in your lab, you are not going to do that. Our lab attendant does that and give you the result. So we're not discussing about that thing. However, the next one is the determination. Okay, so another process is like you can also determine some insoluble solid by passing the water through the filter paper. Again, you have to weigh the filter paper before and let the pass the substance there, see if something is on the filter paper, then put it in the desiccator, dry it, and take the weight again and find the solids. And in that matter, you will also find the undissolved solids, and you can also subtract the dissolved solid, so find out the total amount of solid. Okay, so that's very physical method, nothing, no chemistry there. However, the fourth experiment in this series is the determination of dissolved oxygen in water, which we will discuss in details in our discussion with our slides. And we need some chemistry here, and there are a lot of chemical reaction will be going on, and we'll take advantage of some reaction. Previously, we actually prevented that side reaction to happen when we use the similar method for some other thing, like when you find out the copper content or nickel or other things by iodometry, iron content, we avoided this side reaction to happen. But now we will let the side reaction to become the main reaction in this procedure. We'll talk about that later. Now, the fifth reaction, or the fifth experiment in this series is the determination of acidity and alkalinity of the water. This experiment also will be not discussing in our main discussion in our slides, because this thing you already know how to do that. It's just simply acid-base titration. The only thing differ here is that you already take two reagents like hydrochloric acid and sodium hydroxide. So to find out the alkalinity, you have to titrate it with hydrochloric acid. So why you have to do that? Because remember, the water in natural sources, you can have natural buffering system. That means you might have some weak acid and weak base dissolved in the sample water in natural water. So you have to find out their alkalinity and acidity. To do that, you will use these reagents which are already standardized. Hydrochloric acid and sodium hydroxide, you know, both of them are secondary standard. So you have to first standardize them to use them in the next experiment. However, you have to choose the indicator according to your acid or base. If you are using a strong base, remember the water is having weak acid. And when you are using strong acid, the water is having weak base. Okay, so depending on the strong acid or strong base, you can choose your indicator. If you're using strong acid, you have to choose something that will give a color change below pH 3.5 or something like that. So you choose methyl orange when you are using hydrochloric acid. When you are using sodium hydroxide, you have to choose the indicator which will change the color at high pH above 10. Okay, so and we know that above 10 the phenolphthalein becomes pink. So for sodium hydroxide titration you will use phenolphthalein indicator, and you can see that this is how you will do the titration for the acid. You will with the hydrochloric acid you will add the methyl orange indicator in the water sample. You will take 50 ml, and this is like the same old acid base kind of titration. Okay, now here the basicity is coming from the dissolved calcium carbonate. Calcium carbonate is a basic salt. Okay, so you'll get that. Now acidity, you will use the sodium hydroxide and you will use the phenolphthalein. And why? It's because the presence of halides, sulfates, nitrates, all these uh, anions can also produce in the reaction with other things some proton. So you have to find out how much free proton is present there. So the acidity of the sample can be estimated by the titration with standard sodium hydroxide solution. And you already know how to do this titration and how to do the calculation of the acidity and alkalinity. They are the same thing. Okay, you have to just find out how much concentration of the H plus or OH minus is present in this water sample. Okay, so that's not a very difficult thing. So we'll be also not going over the acid base titration again, because this titration you have done so many times. We don't have to worry about these things. You can do them. So we'll be mainly discussing here about the this one, determination of dissolved oxygen in water. So do you have any question about the acidity and determination of the acidity and alkalinity of the water? Anyone have any question about these two things?
ম্যাম ক্যালকুলেশনটা ক্যালসিয়াম কার্বনেটের রেসপেক্টে কেন নেওয়া হচ্ছে?
Calculation to calcium carbonate respect and also because we are thinking that the alkalinity that we are seeing here is because of the calcium carbonate. And for the second one, actually for the acidity also, so again we are thinking that it's the calcium ion that's maybe interacting with the water and producing this H plus. So that's why both of the cases we are calculating it in terms of calcium carbonate, because that could be the main source of the mineral in our water sample. Okay, so that's why we are doing all this calculation in terms of calcium carbonate. Okay, because that's the buffer system. Actually, this is the buffer system in our one is the calcium carbonate, other is the carbonic acid. If you remember, the carbon dioxide can also get dissolved in the water and can form a carbonic acid. So that calcium carbonate and the carbonic acid can also produce bicarbonate. Okay, bicarbonate ion present in the water. So that will form the buffer system in the aqueous solution, natural aqueous solution. I think I asked you in the last class is like you have seen the acid rain, but why the acid rain doesn't cause much change in the river system pH, okay, compared to the if you add some acid in the DI water. It's because the natural water system has some natural buffering, and mainly this natural buffering comes from calcium carbonate, and calcium carbonate then reacts with the water. The carbon dioxide also gets dissolved on the water and forms hydrogen carbonate. So it can have a excuse me, a buffer system, either carbonic acid hydrogen carbonate or hydrogen carbonate calcium carbonate. So that's why we are calculating all of this calculation in terms of calcium carbonate. Is it clear now?
Yes, ma'am.
Okay, so that's the alkalinity and acidity for the water, and we will be going to the determination of dissolved oxygen in water. Do you remember any experiment where you had problem with the dissolved oxygen, or the term dissolved oxygen came in those experiments? you have done some experiment as 112 also, right? As 116. So can you remember any of the experiment where you had a problem with dissolved oxygen? রোল নাম্বার 1 আজকে আছো দেখি, এখন প্রেজেন্ট আছো? রোল নাম্বার 1 আচ্ছা, তুমি হচ্ছে 112 কিংবা 116 এমন কোনো এক্সপেরিমেন্টের কথা বলতে পারবে যেখানে আমাদের ডিসলভ অক্সিজেন একটা প্রবলেম ছিল?
আরেকবার ম্যাম, বুঝতে পারিনি।
আচ্ছা, এমন কোনো এক্সপেরিমেন্টের নাম বলতে পারবে যেখানে আমাদের ডিসলভ অক্সিজেন সংক্রান্ত কোনো ধরনের সমস্যা ছিল, যে ডিসলভ অক্সিজেন থাকলে আমাদের এই প্রিকশন নিতে হবে?
আমরা ডিজেল অক্সিজেন বের করছি
হ্যাঁ হ্যাঁ,
নেটে, অনলাইনে যেটা প্রথম টেস্ট ছিল ওইটাতে ডিজলভ অক্সিজেনই বের করছি আমরা। তো
অনলাইনে প্রথম এক্সপেরিমেন্টে কবে আমরা ডিসলভ অক্সিজেন বের করলাম?
এটা তো কুইজ ছিল তোমাদের, ওই যে ধরো শর্ট একটা টেস্ট আর কি, যে ওইরকম কিছু ছিল, ওইটার কথা বলতেছো? একবারে প্রথম
হ্যাঁ
দিন
হ্যাঁ
সেফটির উপরে
হ্যাঁ, জি স্যার, ওইটা।
ওইখানে ডিজলভ অক্সিজেন বের করা হয়েছে। তোমরা আয়োডোমেট্রিক টাইট্রেশন করো না? আয়োডোমেট্রিক টাইট্রেশন
জি স্যার, করছি।
আর কি বলবো, এখন চিন্তা ভাবনা করো।
সেটাই, কেউ বলতে পারবে এখন? আচ্ছা ঠিক আছে, বোঝা যাচ্ছে যে তুমি অতটা মনোযোগ দেয় নাই। আচ্ছা, রোল নাম্বার 2।
ইয়েস ম্যাম।
ওকে, সো তুমি বলতে পারবে যে হচ্ছে আমাদের ডিসলভ অক্সিজেন সংক্রান্ত কি সমস্যা ছিল কোন এক্সপেরিমেন্টে?
ম্যাম বলতে পারবো না ম্যাম, মনে নেই।
বলতে পারবে না? অলরেডি কিন্তু স্যার তোমাদেরকে হিন্টস দিচ্ছে, তারপরে পারতেছো না। আচ্ছা ঠিক আছে, রোল নাম্বার 3।
অনেক আগে করছিলাম তো ম্যাম, ভুলে গেছি।
তাই?
মাঝখানে বড় গ্যাপও ছিল, এই কারণে আর কি সমস্যা হয়েছে।
আচ্ছা, রোল নাম্বার 3 পার্থ সার্থী পাল, আছো? আচ্ছা, রোল নাম্বার 5 নুজহাত তাবাসসুম,
ইয়েস ম্যাম।
তোমার মনে আছে কোনটা সম্পর্কে এরকম?
ম্যাম আয়োডোমেট্রি মনে আছে, বাট এক্সাক্ট এক্সপেরিমেন্টটা মনে নেই।
আচ্ছা, এক্সপেরিমেন্টটা মনে না থাকুক, কিছু প্রিকশন ছিল মনে আছে সেখানে আয়োডোমেট্রিতে? আচ্ছা, আমি
ম্যাম ম্যাঙ্গানিজ সালফেট কেন হয়েছিল?
ম্যাঙ্গানিজ সালফেট দিয়ে কিছু করো নাই তোমরা এর আগে? যেটা করেছো সেটা হচ্ছে যে ওই যে যেটা কি বলে, ওই ইডিটিএ কে হচ্ছে যে করা, কি বলে, স্ট্যান্ডার্ডাইজ করা, তোমরা করো নাই। আমি জাস্ট বলেছি 1 নম্বর, কিন্তু আমি যে এক্সপেরিমেন্টের কথা বলছি সেটা তোমরা করে আসছো ল্যাবে।
ম্যাম অন্ধকার রুমে রাখতে হয়।
অন্ধকার, গুড। এখন অন্ধকার রুমে রেখেছিলাম, এবং কিসের জন্য? থায়োসালফেটকে স্ট্যান্ডার্ডাইজ করার জন্য, তাই না? কিন্তু রিঅ্যাকশনটা ছিল কি? থায়োসালফেটকে তোমরা স্ট্যান্ডার্ডাইজ করেছো কাকে দিয়ে? মনে আছে? পটাশিয়াম ডাইক্রোমেট দিয়ে।
জি ম্যাডাম।
কিন্তু এই রিঅ্যাকশনটা ডিরেক্টলি করা যাচ্ছিল না, সো উই হ্যাভ টু গো থ্রু আয়োডোমেট্রি, তাই না? এবং আয়োডোমেট্রি দিয়ে যেহেতু করছিলাম সেই জন্য হচ্ছিল আয়োডোমেট্রি কি বলো? আচ্ছা তুমি না, আরেকজন বলবে। আনিকা তাসনিম, বলো আয়োডোমেট্রি কি? আনিকা তাসনিম, আছো? ঘুমায় নাকি এরা অন করে আল্লাহ জানে। আচ্ছা, ভাস্কর কান্তি রায়।
ইয়েস ম্যাম।
ও তুমি তো বলছিলা না, তুমি না। তাহমিদ সাদিক, তাহমিদ সাদিক, চুপ করে আছো না ঘুমাচ্ছ বলো তো? কাউসার, তোমার কি মনে হয় এরা কি আছে ক্লাসে?
ম্যাডাম এখন আগের দিন তো একটা প্রুফ পাওয়া গেল যে একজন ঘুমায় গেছে, এখন আসলে ওইরকম কয়জন আছে, কারণ আমার মনে হয় ঘুমের মধ্যে আছে কয়েকজন, এটা এখন বোঝাই যাচ্ছে।
সেটাই। মোহাম্মদ মাকসুদুর রহমান আছো? তোমাদের ক্লাস পারফরমেন্সে কিন্তু মার্কস আছে তাই না? সো এরকম ডেকে না পাইলে কিভাবে মার্কস দেবো?
এগুলো তো রেকর্ডেড থাকতেছে, আমাদের কাছে তো ডকুমেন্ট থাকতেছে যে এই যে রেকর্ডেড, তোমাদেরকে খুঁজে পাওয়া যাচ্ছে না, তো ক্লাস পারফরমেন্সের মার্কটা যাবে কোথায়? মানে তোমাদের এখানে তো একটা পোর্শন আছে মার্কের, এরকম রেসপন্স যদি না থাকে।
আর এটা এত মানে সিম্পল, মানে কি বলবো, এটা এতবার বলা হয়েছে জিনিসটা, আর এত ইম্পর্টেন্ট একটা ইস্যু, হ্যাঁ, আয়োডোমেট্রিতে, এই জন্য বারবার বলছি। আবার মোহাম্মদ মাকসুদুর রহমান আছো? ওকে, আমি মুভ করছি। মাহমুদ হোসেন, মাহমুদ হোসেন মাসুম।
কি অবস্থা ম্যাডাম, মানে কতগুলা স্টুডেন্টের।
কে এটা? মাহমুদ হোসেন আছো? নাই। আচ্ছা, ওর মাইক্রোফোন কি অন তো মনে হচ্ছে। আচ্ছা, মাহমুদ হাসান, সরি মাহমুদ হোসেন। হ্যাঁ হ্যাঁ, আচ্ছা, আয়োডোমেট্রি বলো।
ম্যাম আয়োডিন সলিউশন ইউজ করে ওইটাকে মানে একটা
আয়োডিন সরাসরি ইউজ করবে?
আয়োডিনের সলিউশন।
আয়োডিনের সলিউশন, আয়োডিনের সলিউশন বলতে কি মলিকুলার আয়োডিন, লাইক I2?
Ma'am, can I tell?
Yes, Tasneem
Yes,
বলো।
ma'am. Yes, ma'am. The process where an iodide salt is used and from where free iodine is obtained, and that is used for titration. It is known as
Good.
iodometry.
Okay,
Like
that's
potassium
good.
iodide is used first. Then the freed iodine is reacted with sodium thiosulfate for determining the concentration of any other substance.
আচ্ছা, ঠিক আছে, গুড। সো ও বলে দিল তোমাদের যে আয়োডোমেট্রিটা কি, যেখানে where we use and salt of iodine, that means you have iodide in your system, and then something has to oxidize that iodide into iodine. So the liberated iodine will be again reduced by another reagent, okay? And this reaction has to be stoichiometrically determinable. So you can use the amount of iodine that's been released from some known volume of substance, and then that will be reduced again back by another reagent with its known volume. And from the chemical reactions and the stoichiometry, you can find out how many of the analyte was present in that solution when it reacted with the either iodide or with the iodine. So that's the iodimetry. So if you don't remember the iodometry, it's really problematic because we have done so many experiments on this. Okay, now I'll move to our today's experiment and I'll ask you question during our conversation, okay? Okay, so what we are having here, this experiment, we are going to determine, okay, one second. Okay. Okay, so now you can see it. Can you see my screen?
হ্যাঁ ম্যাডাম, দেখা যাচ্ছে।
Yes, ma'am, দেখা যাচ্ছে।
So what you're
Yes,
seeing
ma'am.
here is the water. Water is a polar molecule, you can see. They're having their hydrogen bonds. Now, what is this thing? This dry molecular substance? Any idea?
Oxygen.
Right?
Ma'am,
So
dissolved oxygen.
dissolve oxygen. So what do you think? How much solubility of oxygen will have in water? You know about their bonding, right? They are covalently bonded substances. So what is the difference between oxygen and the water? Anyone?
Polar or non-polar?
Good. Oxygen is non-polar and water is polar. So what does the solubility law say to you? Is it going to be very soluble in water? No.
Less
Okay. Less soluble in water. And therefore it's very important because oxygen is a very important element or gaseous substance for any aerobic life to exist, right? We breathe oxygen, and so are so many different organisms, fish, all the aquatic aquatic life forms, they take oxygen for their aerobic redox process to break their food and produce energy. Okay, so all the organisms which depends on oxygen need oxygen, and so the amount of dissolved oxygen is very important for to understand the aquatic life form and their healthy environment. Okay, so we can see that as oxygen is first of all is gas, second of all it's a non-polar substance, so it has very low solubility in water, and this solubility is also depends on some other physical parameters we'll see later. And therefore, to find out the water quality, if the water is good enough for aquatic life form, or we are going on a verge of a catastrophic disaster because of the depletion of oxygen from the water, we have to do this analysis to find out the oxygen level in water. Okay, and as you can see, what oxygen is not very soluble in water. So although we have about 21% oxygen in the air, so 21% means you can also find it out in weight by volume or gram by volume, volume by volume. All this manner is like if you take 100 gram of substance, you'll find 100 gram of air, you will find 21 gram of that air is oxygen. Okay, but the amount of oxygen in water is so small is that we describe the water quantity or water content in water by ppm, parts per million. Okay, parts per million, can anyone tell me what is the parts per million? We have talked about that in the last class also. What is the parts per million? When you have কতটুকু থাকবে?
ম্যাম 1 লিটারে কত মিলিগ্রাম দ্রবীভূত আছে?
Milligram per liter. That means it's such a small
milligram
amount.
per liter.
Okay, so you can see it's such a small amount. আমরা এয়ারে যখন ব্রিথ করছি তখন আমরা পার্সেন্টেজে পাচ্ছি, তাই না? 21%. That's huge amount. But in water it's becoming ppm. So that's very small amount, but it's very crucial. Okay. So the objective is just simply determination of the presence of dissolved oxygen in water. So this is like the the qualitative analysis, how you can find the presence of the dissolved oxygen in water. Okay, if you know that the dissolved oxygen reacts with potassium iodide in the presence of acid. So if you just do that experiment, you can find that, okay, there is some dissolved oxygen present there, if you can see that brown color form. However, we are not just stopping there. Our main purpose is to application of iodometry in determination of the dissolved oxygen content in water sample by titration. Sorry about that, just water samples. You don't have to write it by. Okay, so this is the application. So main objective is to actually determine the amount of dissolved oxygen content. However, we are going to do it by applying the iodometry. Okay, iodometry. And the dissolved oxygen in short form is written as DO, is expressed in terms of milligram of oxygen per liter, that is mg per L, or percentage of air saturation is not used that much in our purpose. However, this is the one which is used commonly, that is the ppm, or 1 milligram per liter. Okay, so these two are same thing, it's just given the definition of the ppm. Okay, so here is a picture. You can see why it's so important, because the oxygen is coming to this water from an equilibrium that's been established between the air and the water. Okay, so mixing by wind, you can see in the surface you have more oxygen saturated water. However, as you go down, you can see there is a less amount of oxygen present in different depth of the water body. So as a chemical engineering student, you need to know how to do the sampling as well as to do the finding out the amount. Okay, so the sampling is very important for this kind of environmental sample. You have to determine which layer oxygen you want to determine. So there can be depth until where the saturation is good amount, so the surface water, or inside up in some depth or some more depth like that. And you can see as you go down and down, you have low oxygen region. So that's why it's important when you are sampling these things, you use a special kind of sampling vessel, which will only open at certain depth. That means you can control the stopper of that bottle. Okay, you can do simply by putting a Winkler bottle. We will see what those bottles are and make sure that it's only open when it goes down, and that nothing else can go inside when it's filled with that water sample. However, what we give you typically is a surface water sample. Okay, from a pond next to Buet, and our lab attendant takes a bucket, which can be airtight, and they first dip the bucket inside the surface water and rinse the bucket with that water. That means take some water and take it out, and then again dip it nicely, and without getting any air inside, they take only the water up to the mark and then close the lid immediately so that it doesn't get any air from the outside of this water surface. Okay, so that's very, very crucial, so that you don't introduce excess air from the other sources. You're just taking the sample only from the water. Okay, so you can see these different life forms are using the oxygen for different purposes. You can have live things that's using the oxygen. You can also have degraded products or the leftover things like dead bodies of the fish and other things, which also needs oxygen to get oxidized and become simpler molecules or simpler substances, which can be water soluble and can be used as nutrients. Okay, so all of this kind of chemistry is going on there, and there are some other planktons and things which can also do photosynthesis, and they are actually, when they do the photosynthesis, they are producing the oxygen also. So they helps the oxygen level to remain something more saturated by their photosynthesis. However, if they die, they also has to go through the degradation process, and the degradation processes are typically all oxidation process, so they all need oxygen. So there are some biological oxygen demand, or you can see some biochemical oxygen demand, and we have to know what are these things are going on in aquatic chemistry, so that we know the environment of this aqueous body. So you not only calculate the dissolved oxygen content, but sometimes what we do, we take this dissolved oxygen amount over the time, say for a 5-day period, okay, one day by another day, and see how much changes is happening if you think some plankton is present in the water body, and how much of them are present in there. That also important for water quality. Okay, so you can see that the dissolved oxygen analysis is a very important tool for water quality, and also to forecast about the health, how healthy the water system is when you have different level of oxygen. It's very important. However, the factors that can affect the dissolved oxygen levels are the surface area, temperature, salinity, pressure, level of organic activity. Now, these things are like how much oxygen can be soluble in the water, that can determined by these things. But the last one is like the water can get oxygen, but it's something that's taking all the oxygen or using the oxygen to produce some other product. So that's chemical reaction that's going to be happening with these things. And these are physical properties that's controlling the solution process. And this is the chemical process which are using it or converting it into some other product. So typically, if you have a good quality water, it will have a dissolved oxygen value range from 5 to 8 milligram per liter. So you can say 5 to 8 ppm. If you have that dissolved oxygen amount, you can say it's good quality water for aquatic life. Now, if you have something below 5 milligram per liter, like 4 milligram or something, the aquatic organism will become stressed. Okay, they will start to feel the problem. And if it goes down below 2 milligram per liter, they will become hypoxic water. That means they will start to feel asphyxiated, and they will get asphyxiated and they will get killed. And you have heard about sometimes there is a like mass fish killing happening some places. The fishes are coming out on the surface dead. Okay, and there could be some very other reason, but all those reasons actually what they cause depletion of the dissolved oxygen. It can be chemically done or it can be happening naturally if you have eutrophic system. Have you heard about this term, eutrophication? শুনেছো? Have you heard about eutrophication? Anyone?
No, ma'am.
আচ্ছা, it's very important. তোমরা 2016 কিংবা 17 একটা ঘটনার কথা কি তোমাদের মনে আছে যে হচ্ছে হাওড় এলাকায়, কারো বাড়ি আছে হাওড় এলাকায়, সিলেটের হাওড় এলাকায়?
আমার গ্রামের বাড়ি পেছনে একটা হাওড় আছে।
আচ্ছা আচ্ছা, ওখানে হচ্ছে 2017 সালে খুব সম্ভবত ওই সময় কি হয়, তোমার ফেব্রুয়ারির শেষের দিকে বেশ কিছু এবং মার্চের প্রথম দিকে হচ্ছে তোমার আর্লি রেইন হয় প্রচুর, তাই না? এরপর বেশ কিছুটা সময় হচ্ছে ড্রাই পিরিয়ড যায় এবং এরপরে হঠাৎ করে দেখা যায় যে হচ্ছে সেই সময় হচ্ছে ফ্ল্যাশ ফ্লাড তৈরি হয়। খুব সম্ভবত পাহাড় থেকে পানি এসে ফ্ল্যাশ ফ্লাড তৈরি করে এবং হচ্ছে সমস্ত যে ইয়েগুলো তোমার ওই সেখানকার যত হচ্ছে তোমার যে সময় পানি থাকে না সে সময় ওখানে হচ্ছে বিভিন্ন ধরনের চাষ করা হয়, তাই না? তো সমস্ত ক্ষেত সহ হচ্ছে সবকিছু পানির নিচে তলিয়ে যায়। এর ফলে কি হয়, প্রায় 15 থেকে 21 দিন পরে দেখা যায় যে ওই এলাকায় প্রচুর মাছ, হাওড়ে প্রচুর মাছ, তোমরা হয়তো দেখেছো, প্রথম আলো, ডেইলি স্টার এরা সবাই হচ্ছে রিপোর্ট করেছিল, তাই না? প্রচুর মাছ হচ্ছে মরে ভেসে। আর হচ্ছে সাথে সাথে কি, সাথে সাথে আরো একটা ইন্টারেস্টিং জিনিস ঘটেছিল এবার, শুধু মাছ মরে নাই, আরো কিছু জিনিস যেমন কিছু গরু টরু এরা যারা পানি খেয়েছে ওই হাওড় এলাকা থেকে, সেগুলো অসুস্থ হয়ে গেছে কিংবা মারা গেছে। বেশ কিছু এরকম কেসও ঘটেছে, তাই না? তোমাদের কি মনে আছে? বা যারা ওখানে আছো তাদের হয়তো মনে থাকতে পারে। এখন এটা কিন্তু খুবই একটা কি বলবো, এটা একটা প্রবলেমেটিক থিং এবং আমাদের দেশে এটা যদিও নতুন না, তারপর ওভার হচ্ছে প্রথম সবচেয়ে এত বেশি বিশাল পরিমাণে হচ্ছে তোমার চোখে আসে, মানে চোখে পড়ে সবার। কিন্তু this kind of things happens all over the world. You might have heard some places in the ocean that has become like dead zone. Have you heard about these names, dead zones, in like Mexican Gulf, next to US? Large area become dead zones, and there are some places around the Great Lakes in US, like Lake Erie and other stuff, where the like sweet water, not the salt water, fresh water system that's also have this kind of problem. So the same problem happened in the Howard area too. There was a lot of other hypothesis, but actually when we find out the reason, we actually did the dissolved oxygen amount and biological oxygen demand, like how much BOD was there and what kind of things were growing there. And we found is that Howard become eutrophic because it had all those fertilizers and other stuff that was put on the field, and it submerged with the water with all these things, and so water body overly enriched by phosphates. These are nutrients. Remember, we all need nitrogen and phosphorus based molecules because these are the building blocks of our DNA. Okay, so does the bacteria, and one specific kind of bacteria is known as cyanobacteria, or they also known as blue-green algae. They are not just simple algae, they are actually bacteria, and that's what happened in the Howard area. The blue-green algae were excessive, it's called in bloom. It's called a bloom situation that happened, and those blue-green algae or the cyanobacteria, they are not so innocent. They can also produce toxins. So a combination of the overgrown algae and the toxin caused that disaster in the How. Okay, so that's a different story. But typically, if you don't even have the cyanobacteria problem, you can still have excessive algal bloom. Okay, and you have seen a lot of ponds in Bangladesh. It looks like this. তাই না? দেখেছো না? So when it happens like this, that means that you are having so much nutrients, phosphates and nitrates, is that you are having a lot of plant and a lot of algae, that's planktons that are blooming, growing. They have their nutrients. However, they are also, some of them are also aerobic, and cyanobacteria is anaerobic. They actually photosynthetic bacteria. But the problem is, as they grow in so much amount, at some depth, the sunlight doesn't get inside. Okay, so they started to die. And when the mass die-off started, that's when they needed so much oxygen to convert them in their different oxidized product. So that's when they started to deplete the DO. And it happens so fast is that the fishes cannot cope with it, and they die as the DO goes down as low as 0 milligram per liter. Okay, as low as that. We found in our area that DO was less than 1 ppm at some point. Okay, so that means you can see that how much. So if it's become like 2 ppm or something like that, the fishes are going to die, and you see this kind of situation happening. So that's why you can see that it's to monitor the water quality with the dissolved oxygen is so important. And sometimes what happens, these are because of the biological oxygen demand or biochemical oxygen demand. Sometimes what happens, you can also add some chemicals from the chemical industries that's going in the stream, and they also wanted to oxidize. So they will also take the dissolved oxygen and create the same kind of situation, and you'll see a lot of fish are dying and coming out of the ponds. So here are a lot of things about what are the importance. I think you can read them, so I'll be not going over them. These are basically all these things I just told you in different form. It's like so this is the biological oxygen demand or biochemical oxygen demand is important because you need to find out how much algae is growing on there. If you see the BOD is becoming highly excess in amount, you can actually find out the biological oxygen demand from the dissolved oxygen calculation at over 5-day period and with different dilution of the sample. And you can say that this water is going to be going to have a bloom soon, and this can cause this problem. And if you can identify that, then you can actually start to take a remediation, remove the excess phosphate or nitrate, do something. So you have to do these tests at different times. So the determination of dissolved oxygen in water serves as the basis for BOD test. The same test you will be doing. The amount of oxygen found dissolved in the given volume of water at a given temperature and pressure is known as the dissolved oxygen that we already have talked about. The solubility of atmospheric oxygen in fresh water, see salinity, that means seawater will be different. So this is for the fresh water when you don't have too much salinity. The fresh water ranges from 14.6 milligram per liter at 0 degree Celsius to about 7 milligram per liter at 35 degrees Celsius. So for our country, so if you find out a aquatic environment where you are having 7 ppm of dissolved water, that's very good water, very good habitable water, because our pressure is almost 1 atmospheric pressure in Bangladesh. Now, water being the liquid in greatest abundance and importance, the environmental engineers must be concerned with the dissolved oxygen. Okay. We also talked about that the oxygen is poorly soluble in water, and its water is proportional to the partial pressure. So sometimes you can see that the water saturation level is given by the partial pressure of the oxygen. Biochemical oxygen demand, and especially the oxygen saturation level, you can see is given as the partial pressure, especially when it dissolves in your blood. Okay, that's what you see in partial pressures, the saturation thing. Okay, now the biochemical oxygen demand determines the amount of dissolved oxygen needed at certain temperature over a specific time period in a body of water to break down organic material by aerobic biological organisms. Okay, so they just oxidize these organic substances in the help of planktons or other algae or other biological small organisms. So a BOD level of 1 to 2 ppm is considered very good. That's like very good. But water supply with a BOD level 3 to 5 ppm considered moderately clean. If it exceeds that 7 ppm or something, that means your water system has to be clean for the algae. Otherwise, you can have toxins. If the algae is cyanobacteria, you might get toxin in your water supply. Okay, so it's that bad. It is that bad. And sometime in Australia, I think sometimes they had to shut down their water supply system because of the cyanobacterial bloom that exceeded this level. Okay, so the change of DO concentration is usually measured over a given period of time in water samples at a specific temperature. It's just same thing. So this is like how the things are going. Now, CO, this is for the BOD. COD. Now, there is another things like chemical oxygen demand is that it's not a live thing that you are oxidizing. It's something from the chemical industry or for chemical that's not originated from life. Coming to your as a pollutant to your water. So chemical oxygen demand is an indicative measure of the amount of oxygen that can be consumed by the reactions in a measured solution. The most common application of COD, chemical oxygen demand, is in quantifying the amount of oxidizable pollutants and found in the surface water. Typically, who has to do it more is the chemical industries. We have a lot of textiles. Textiles has to do this COD analysis all the time before they can release the their water, their wastewater to the environment. Okay. So chemical oxygen demand is used to determine the quantity of pollution in water after wastewater treatment, and also like if they have set up a plant to clean their wastewater, how much is actually it's working. You can find out after it's ran through that treatment plant. If you take the sample and find out that it has been improved by removing, lowering down the COD or chemical oxygen demand. So the higher value of the chemical oxygen demand, COD, indicates the higher organic pollution in the wastewater sample. Not only organic, there are lots of other pollutant which can get oxidized. Only chemically digestible matters can be determined by COD test. The chemical oxygen demand method determines the quantity of oxygen required to oxidize the organic matter in a waste sample under specific conditions of oxidizing agents, temperature, and time. Okay, we use a different method to find the chemical oxygen demand, not the method we are going to talk now. This method is typically used to find out dissolved oxygen and BOD. Okay, so these are other methods that you can use to find out the dissolved oxygen. However, the problem with this method, like the colorimetric method, is that it's expensive. Okay, you need to have a good instrument which is very expensive instrument like UV spectrophotometer or something like that. You can also have sensor method, but for that also you need these instruments. You cannot do them just like on field or things like that. So these are not very economically viable. However, tachymetric method, as you can see, is much cheap. So we can use that to find out our dissolved oxygen. And most important one is the Winkler's method that we are going to talk here now. You can also use slightly modified Winkler method that's sometimes also used in the lab, especially if you are doing, it's like for your thesis or research, you'll be doing that. It's just to remove the nitrate or nitrite in the sample water. As you can see, we also use a lot of fertilizer these days, and which introduces a lot of nitrates in the water. And if the nitrates are present in the water, they can also interfere in the process, because the tachymetric method we are going to use here, Winkler's method or other, they are all redox titration, right? So redox titration e hocche nitrate thakle সমস্যা করবে. So that's why we want to remove that by the azide. However, we will be not discussing about this one here. We will be just talking about the Winkler, the original method of finding out the dissolved oxygen in any kind of water source, especially if it's clean. That means it doesn't have much dissolved solid. It's not murky. ঠিক আছে, ঘোলাটে কাদাটে না, ফ্রেশ ওয়াটার। এখান থেকে হচ্ছে তোমার dissolved oxygen content বের করার জন্য সবচেয়ে ভালো হচ্ছে Winkler method। ভালো বলতে হচ্ছে cheaper and ভালো। আচ্ছা, the conventional Winkler method was first invented by this Hungarian scientist, I think in late 18th century. So this method can only be used only for estimating dissolved oxygen content in clean water. Okay, and we assume that these are free from iron, nitrates, or other organic matter. Now, what you do in this method? It's an iodometric titration method. Okay, so we need the potassium iodide. And another important things are these bottles. These bottles actually Winkler, also known as the Winkler bottle. So he actually came up with this bottle for this specific reaction, specific experiment here. What you can see here, this bottle has this mouth which needs a ground glass joint. দেখতে পাচ্ছ যে ground glass joint এবং the stopper also have this kind of ground glass feature. It makes this bottle airtight. Okay, that's why, because you need to make it airtight when you are doing your reactions and when you have your sample. No air can come from the outside. If you can get the air from the outside, that will change the oxygen level inside the sample, right? So that's why you need to make sure that you are not getting air from the outside. So what you will do, you will have the sample which will have the dissolved oxygen. That will we'll need another things that can interact with the iodide to make it to iodine, and we have to use some oxidizing agent. Now oxidizing agents can be oxidizing and reducing agent depending on what you are doing. Now they can be either dichromate or manganate, things like that. Here we are going to use some manganese salt. However, what we are going to do, we are trying to make a precipitant with it. Okay, so under alkaline pH, this manganese salt will form manganese hydroxide in the presence of iodide ions. And when it does that, it can also interact, the solid manganese hydroxide can interact with the dissolved oxygen and can make manganate, that means manganese plus 4, or it can go through a trivalent manganese MnOH3 and then form the Mn plus 4. So the manganese is going to be this kind of cycling, and with it, it can form iodine, can liberate the iodine. So oxidation of the iodide to free iodine by fixed oxygen under acidic pH. Okay, so when this is happening, when this alkaline pH, you are forming this manganese salt, manganese hydroxide, it can also take the dissolved oxygen and make it a transient compound but also solid, MnO OH2. Well, maybe we'll discuss about it. Yes, we'll discuss about this. So this kind of substance, and then it reacts with acid and forms that first you are having MnOH2, and with the oxygen that's present in the dissolved oxygen will make it MnOH2, and then it will again react with the iodide and make it iodine and make Mn4 plus. Okay, MnO2. That is MnO2. Okay, so you can see there are a lot of oxidation state change, and which is driving the iodide into iodine. So that's a redox system. So, and the iodine is produced under the acidic condition. First you are alkaline manganese salt, then you are changing the pH to acidic pH when you are fixing the oxygen in this kind of compound and fixing the oxygen, creating liberated iodine. Okay, so the amount of oxygen will fix, that will transfer into equivalent amount of iodine. And then what you'll do, you'll then do the simple iodometric titration with the thiosulfate, as we have done already. So you will be titrate the produced iodine. So this iodine has to be equivalent amount of iodine equivalent to the oxygen present in the water. So this iodine, now if you know the concentration of the thiosulfate, you can find out how much thiosulfate you have used to convert this iodine into iodide back again. That's a very nice stoichiometric relationship between these two reactions, and you can use that to find out how much of the dissolved oxygen was used to produce this much of iodine. So from that you can find out the amount of oxygen. Sorry about that. So you can see this is the whole process, and in iodometric titration we'll be using starch as the indicator, and we'll look at each of the steps separately. Okay, so the theoretical background is the Winkler method is used to determine dissolved oxygen content in water. We already talked about. The method uses chemical reaction. So this is the theory you have to write in your report. The method uses chemical reactions that releases an amount of iodine, okay, defined amount of iodine equivalent to the amount of oxygen originally present in the water sample. And that's why we need that special bottle, so that we don't have the sample come in contact with the air, and the oxygen can have a diffusion process to get dissolved in the sample water. With subsequent measurement of the amount of iodine released by means of a standard solution of a reducing agent. Okay, so that's the typical. So dissolved oxygen can oxidize divalent manganese ions Mn2 plus to tetravalent manganese ions Mn4 plus in the presence of strong alkali. Okay, so this is in the alkaline medium. Remember, in acidic medium, what would happen is that this reaction will start to become reversible. So initially we want to convert the manganese to Mn4 plus with the dissolved oxygen. That will interact with the iodine. So the tetravalent manganese 4 plus is again reduced to divalent Mn2 plus in the presence of a strong acid. And that's what you always see, like if you have manganese 7 plus permanganate, that's going to be Mn2 plus, just one product if you have strong acid in the presence of potassium iodide. However, so first we are making it Mn4 plus, so we are oxidizing it as we need it so that we can get an equivalent amount of reaction, and then it will take 2 electrons and become Mn2 plus in acidic condition. So when it does that, liberating an equal amount of free iodine from the iodide solution. So you also have to give iodide to that. So the quantity of iodine liberated will be proportional to the quantity of dissolved oxygen present. When we see that chemical reactions, that will become more visible to you. The iodine can be estimated by titrating with a standard solution of sodium thiosulfate using starch as an indicator. Do you remember the formula of sodium thiosulfate? Can anyone tell me the formula of sodium thiosulfate? Roll number 15.
Na2H2O3
গুড। আর এটা হচ্ছে রিডিউস হয়ে কি তৈরি, এটা সরি এটা তো রিডিউসিং এজেন্ট হিসেবে কাজ করবে, কাজে অক্সিডাইজ হয়ে কি তৈরি করবে?
সোডিয়াম টেট্রাথায়োনেট।
আর সোডিয়াম টেট্রাথায়োনেটের কি সংকেত কি?
Na2S4O6।
আচ্ছা, নাও রোল নাম্বার 16, আর ইউ প্রেজেন্ট?
Yes, ma'am.
আচ্ছা, সোডিয়াম টেট্রাথায়োনেটে বা টেট্রাথায়োনেটে সালফারের অক্সিডেশন স্টেট কত?
Ma'am, +5.
হ্যাঁ
ম্যাম কোয়েশ্চেনটা একবার করা যাবে?
হ্যাঁ, সো টেট্রাথায়োনেট মানে S4O6 2- এই আয়নে সালফারের অক্সিডেশন স্টেট কত?
ম্যাম
আচ্ছা, থায়োসালফেটের সালফারের অক্সিডেশন স্টেট কত ছিল, কে বলতে পারবে?
ম্যাম 5।
আচ্ছা হ্যাঁ, আর টেট্রাথায়োনেটে
2.5
ঠিক আছে 2.5. Okay, so that means it's being oxidized. Okay, so when interference from nitrates is present, it is impossible to obtain a permanent endpoint. So what happens if you have nitrates? You are using starch as the indicator, and if you have nitrate will keep reacting with the will keep reacting with the potassium iodide, and it will oxidize the iodide into iodine. So the iodine individuated is not only from the oxygen here, also from the nitrate can also happen. So that's why we need to remove the nitrite. But we are not going to use the azide here. What you will be doing here is just using the alkaline potassium iodide. We are not doing that. You can also add a little bit azide with your mixture when you are adding the potassium iodide and the alkaline potassium iodide. That will take care of the nitrite and will liberate the nitrogen. So it will not actually hamper any of the reaction and will not disturb the reaction. That's what it does, just do, the azide. Okay. Okay, so you can use the sodium azide and just with this alkali potassium iodide, that will take care of the nitrate. Now let's see. The principle involves in the determination of the dissolved oxygen in water is to oxidize an equivalent amount of potassium iodide to iodine by the dissolved oxygen. So what you are doing here, you are making this, okay, let's not write the I. Okay, I-, right? You are making it to I2. So this is the simple iodometry, right? You make it that and then you convert it back again I-. Here you have the oxidizing agent will be, we want to use the oxidizing agent, the O2, and here you have the S2O3. Okay, so this is the whole reaction actually, what is happening here. But you have to use some other ingredients, some other chemicals to do this reaction. Now you are using manganese sulfate and sodium hydroxide as an intermediate reagent to help this process, to help the oxygen to interact with the iodide to produce iodine. The basic manganese oxide formed from manganese sulfate and sodium hydroxide acts as oxygen carrier and brings the dissolved oxygen into the nascent form to take part in the reaction. Nascent form means, nascent form কি অক্সিজেনের বলো তো? আরেকটা নাম আছে nascent form-এর, এরকম ভাবে দেখানো হয় না, থার্ড ব্র্যাকেটের মতো অক্সিজেন,
জায়মান অক্সিজেন,
জায়মান oxygen by atomic oxygen, right? It's very reactive. It will react, it will oxidize anything immediately, right? Because it doesn't have the saturated, doesn't have the octet, so it will react immediately. So that's what it's do. It's actually convert the molecular oxygen into this form. So that, and it's very transient. As soon as it forms, it interacts. Okay, so to provide this or to create this from the oxygen, we are using manganese sulfate in sodium hydroxide solution. In alkaline manganese solution, manganese can do that. Okay, so this is the process. The first, the manganese sulfate, this is 2+, right? It's forming the manganese hydroxide. There is nothing, it's just a simple, what you can say, প্রতিস্থাপন বিক্রিয়া, তাই না? আর কিছু না এখানে, আর কিছু হচ্ছে না. Nothing else is happening here. No oxidation number or anything is changing here. Just a simple. But what you are having here, the manganese hydroxide, what kind of compound is this? Is it soluble or what? Hydroxide. Hydroxides are typically, I don't know if you have seen the solubility laws, okay? Hydroxides, ionic substances are not soluble unless you have specific cation with them, like sodium hydroxide. It could be like the alkali metals, they are like the all soluble, either them or special cation is present, then only hydroxides are soluble. And manganese is not that special cation. So manganese hydroxide is not going to be soluble. So it will come out as a precipitate. ঠিক আছে? Okay, so the next step. So what we have to do, we have to add the sodium sulfate in the alkaline sodium sulfate in our water system. Or as soon as we do that, we add this manganese sulfate, sodium hydroxide. First we add the manganese sulfate. Manganese sulfate is soluble in water. It makes a pink color solution. So we add that, and if we add the sodium hydroxide to it, it will form a solid precipitate. Its color is very pale pinkish white. You can say it's white. Manganese hydroxide is white. Okay, that precipitate. So now, then this manganese hydroxide, it's a manganese, right? It doesn't like to be in 2+. It's like to get oxidized. It's a transition metal. So it has other stable oxidation state in alkaline solution, and in alkaline solution it like to be either trivalent or tetravalent, more oxidized state. So it will interact with the oxygen that present in the water and form this MnOOH2. You can see the 2 moles of manganese hydroxide interact with 1 mole of oxygen to produce 2 mole of MnOOH2. Here, the manganese could be trivalent, or it can also form MnO2. Okay, so different mechanism, different book in different mechanism have different chemical formula of what is compound, because it forms so transiently. And this is also solid. Okay, this is also solid. MnOOH2 is also solid. So it's called the fixation of the oxygen. Okay, so the oxygen is fixed here. Next step, it will have react. So if you add the acid there, then okay, if you add the acid, it can take this oxygen out as the nascent oxygen. Okay, as soon as you are adding the sulfuric acid here, the H+ comes and interact with this, makes this one as the water, and this oxygen comes out, and the manganese becomes reduced again from manganese 4 to manganese 2, and it removes this oxygen as O, or German oxygen. Now this German oxygen can interact with the potassium iodide I- and produce the iodine and water. Okay, with the sulfuric acid you have the enough amount of the H+ protons that interacts with the oxygen, and here you have 2- in the oxygen's oxidation number, and iodine is 0, and here iodine is minus. And what will be the oxidation state of the oxygen here? Anyone? Okay, it's just atomic oxygen. So it takes 2 electrons to become this O-2 minus here. Now, at the ionic reaction. So you can also say that instead of forming that MnOH2, you can also write it in this way as well. Okay, these are solid and fixing the oxygen. Then it reacts with the iodide and makes this iodine and forms the water. Okay, so in oxygen, what is the oxidation number of oxygen?
0.
0. So you can see that it's becoming reduced and the iodide is becoming oxidized. So these are the two half reaction, but that doesn't go in one step. It goes through those intermediates. And finally, when you have produced this iodine in a solution, it's not very soluble in the water, right? It's a covalent compound. To make it soluble, you have already added, you don't add the iodine like a very stoichiometrically. You always add some extra iodide, right? Why? Because this iodine is not soluble in aqueous solution, and you have to titrate the iodine. So make it soluble, you have to add iodide, excess iodide ion, so that it can form. So you can look at it, it forms like this, triiodide ion. Okay, so triiodide ion. What is the shape of this molecule?
Linear.
Linear. এটার হাইব্রিডাইজেশন, সেন্টার অ্যাটমের হাইব্রিডাইজেশন কি হবে, কোথায় বাই করতে পারবা? লুইস স্ট্রাকচার করতে পারো এটা?
Yes, ma'am. sp3d2.
না, sp3d2 না, sp3d।
D, yes, ma'am. দুটা লোন পেয়ার, yes, ma'am.
এবং প্রত্যেকটা ইকুয়েটোরিয়াল পজিশনে হচ্ছে কি লোন পেয়ার।
Lone pair, yes, ma'am.
That's why it's a linear ion. Okay, so linear ion, and it's soluble because it's ion, so it's soluble in water. So, but its color is yellow. Iodine color ki?
Purple.
Purple বা violet. And I3 minus এটার কালার হচ্ছে yellow. Okay, আর এটা বেশি থাকলে, বেশি কনসেন্ট্রেটেড হলে একটা ব্রাউন কালার দেখা যায়। ওকে, যত বেশি থাকবে তত বেশি হচ্ছে ব্রাউন কালার দেখা যাবে। Okay, so let's move on. So you can see the I3 minus, this will actually, the iodine actually comes in the reaction. I minus don't react with the thiosulfate. It reacts with the thiosulfate and produces potassium iodide, the iodide again, the reduced form and oxidized form of tetracyanide. So that's the total reaction. Now, if you can see 1 mole of I3, that means 1 mole of iodine reacting with 2 mole of thiosulfate. So we can get a stoichiometric relation from those reactions, like how many moles of oxygen is reacting here, and that is equivalent to how many moles of iodine is formed. Okay, here, then you are using that here, so you can find the stoichiometric relation among these chemicals. These are the equipments you need. You need the standard manganese sulfate solution. So manganese sulfate is pale pink. If you make it solution, it looks like this, very pretty color. Okay. You need alkali iodine reagent. That means the alkali iodide reagent. That means the iodide is like here, sodium hydroxide, potassium iodide. Then you need the standard sodium thiosulfate solution, okay, in the burette. And you need sulfuric acid. Okay, sulfuric acid. And then you also need this thing, you need a this Winkler bottle or this BOD bottle. They are known both way. This bottle with a ground glass joint. You need volumetric flasks, you need burette, you need pipettes, the simple things for the titration, like you need to set up a titration for like this way. So that are the things you need. Now, let's see what you are going to do. So first take 250 milliliter bottle or 300 ml bottle of that Winkler bottle and filled with water sample. So your water sample will be given in a bucket or in a large beaker, you have to dip. First, what you'll do, you'll take a little bit of the sample water in your Winkler bottle, close the stopper, clean it nicely because it has to be rinsed with that water, and then you dip the whole bottle inside this beaker so that you don't have any air when you're taking the sample. Okay, you have to dip the whole thing, and then take the sample, the water at the top. Okay, পুরোটা যেন ভর্তি হয়ে থাকে এবং কোনো ধরনের বাবল বা বাতাস যেন না ঢুকে, এভাবে হচ্ছে তোমার স্যাম্পলটা নিতে হবে। ওকে, and after you take that, you have to add the stopper before you add anything else when you are preparing something. Then introduce 3 milliliter of oil. There is not written incorrectly. First, you take 1 milliliter of manganese sulfate solution. Now, you can see this is the pipette tip, and I don't know if you can see it, the water level is up to here. Okay, that means you fill it completely. And when you are adding any solution, you have to dip the pipette tip below the surface, way below the surface, like here is the tip of the pipette, way below the surface of the water sample, and actually you pass it through down of the, so that it goes, it doesn't comes on the surface contact. So you add nicely the manganese sulfate. First you add the manganese sulfate, then you take alkaline potassium iodide solution. Okay, and you can see there are some information for you. These are toxic, some are irritant, things like that. So you add very carefully this alkaline potassium iodide solution. Same way you take with another pipette and add the solution below the surface. Okay, and you add about 3 ml of that alkaline solution, potassium iodide solution. This potassium iodide is 15% here by volume. Then what you do, then you put the stopper of this bottle back again and give it a good mix, and you see that the solids, as soon as you are adding this potassium iodide solution, you see the brown precipitate started to form. And when you put the stopper and give a good shake, you see that it's doing good reaction, and you left it to settle down the manganese hydroxide. You can see them. They are actually white, but because of the presence of the iodine, okay, the reaction will be instantaneously. You don't see much iodine here, but they are doing this reaction. So manganese hydroxide reacting, it's forming some German oxygen, that reacting with the some of the potassium iodide, making them some iodine, and that's a triiodide, and they're making this whole thing slightly colored. Okay, but the precipitate is white. You can see it, right? এটা ঘোলাটে হয়ে গেছে, দেখছো না? এরকম ট্রান্সপারেন্ট ছিল যখন এই দুটো জিনিস, ওগুলো ট্রান্সপারেন্ট সলিউশন ছিল, যদি ম্যাঙ্গানিজ সালফেট একটু কালার ছিল, but that was transparent. But when you mix these two, you can see it's like this precipitate is murky একটা কালার চলে আসছে, and you keep it for some time so that at least the 5 centimeter from the top becomes clear and the precipitate settle down in the bottom. ঠিক আছে, এই প্রিসিপিটেট ফর্ম হওয়ার পরে তুমি কিছুক্ষণ রেখে দিবে যাতে হচ্ছে প্রিসিপিটেটটা একটু নিচের দিকে সেটেল করতে থাকে। Okay, so when the upper part of the solution become completely clear, that means at least 5 centimeter from the upper part become clear, add 1 milliliter of concentrated sulfuric acid into the bottom of the bottle using a pipette. Same way পানির সারফেসের নিচে পিপেটটাকে নিয়ে গিয়ে তোমার হচ্ছে যাতে কোনোভাবে যাতে এয়ার যাতে না ঢুকে সেই জন্য এটা করা হচ্ছে। তোমার হচ্ছে 1 ml সালফিউরিক অ্যাসিড অ্যাড করা হচ্ছে, অর্থাৎ আমরা অ্যাসিডিফাই করছি সলিউশনটা। অ্যাসিডিফাই করার সাথে সাথে কি হবে, এই দেখো এটা ছিল হচ্ছে আমার বটলটা। অ্যাকচুয়ালি যখন আমি অ্যাসিডিফাই করা শুরু করব তখনই তুমি দেখতে পাচ্ছ কিছু অংশ ক্লিয়ার হয়ে যাচ্ছে, কিছু অংশ ঘোলাটে হচ্ছে, তার মানে ধীরে ধীরে এই প্রিসিপিটেটটা ডিজলভ হয়ে যাবে। ওকে, প্রিসিপিটেটটা ডিজলভ হবে কেন? কারণ এখন আর হচ্ছে অ্যাসিড অ্যাড করার সাথে সাথে আমার ম্যাঙ্গানিজ হাইড্রোক্সাইড থাকছে না। ম্যাঙ্গানিজ হাইড্রোক্সাইড কিংবা ম্যাঙ্গানিজ অক্সাইড যেটাই হোক, সেটা হচ্ছে এখন কনভার্ট হয়ে ম্যাঙ্গানিজ 2+, অর্থাৎ ম্যাঙ্গানাস ফর্মে চলে আসছে, যেটা হচ্ছে সলিউবল। আর ট্রাইআয়োডাইড তো আগে থেকেই ওয়াটার সলিউবল। So now you'll see, okay, so you again stop the bottle and shake so that it mixes nicely, and you'll see that when you are shaking it, it will become this যে স্টপারটা বন্ধ করে ভালোভাবে শেক করতে হবে। তখন কি দেখবে তুমি, দেখো এখানে কিন্তু সবসময় স্টপারটা এমনভাবে দেওয়া আছে যেন হচ্ছে যে একটু যাতে বাতাস না ঢোকে। Okay, so when you are shaking it, you can see it's getting clear, and at time it become completely clear brown solution. So this brown solution is because of the triiodide ion, and if you have more and more dissolved oxygen, it will be more and more denser in color, in brown color. So the color of this solution is directly proportional to the dissolved oxygen amount of the dissolved oxygen. And then transfer 100 ml of this iodine containing solution carefully into a flask and titrate it with sodium thiosulfate. Okay, so then you take 100 ml from this solution that you have prepared here, the iodine solution. You take 100 ml with a pipette, and already in the burette you will have your thiosulfate, which is standardized, so you know the concentration exactly, and you start to do titration. And you will be using starch as the indicator. So when you are titrating, the color will, as you are adding the thiosulfate, you are shaking it, it will become lighter in color. See the change in the color? It's brown, and here it's lighter yellow. It's color change to বোঝা যাচ্ছে?
জি ম্যাম।
Okay, so যখন এরকম lighter yellow হবে, why we do that? Because we are using starch as the indicator, and starch is not a redox active indicator. It's a complexometric, or it makes an inclusion complex with the iodine or triiodide ion, and that changes the color. If you have added the starch before, like when it's not becoming that light color means you have less iodine here. You have most of them as iodide, right? You have most of them as iodide and very less amount of iodine. That's why the color is light yellow. So starch does one more thing. It's make an inclusion complex with the iodine, and some iodine can get inside the starch's macromolecular structure and can stuck there. Okay, if that happens, you will not get a sharp endpoint. So that's why we add the starch at the end of the reaction when it becomes so light in color. So less amount of iodine in concentration is present. So what happens now? It will become a concentration driven reaction at the end point. Because the iodine is less amount, it cannot be absorbed in much amount with the starch. So it will come out from the starch very easily, because in solution its amount is less. So as you are adding the starch indicator, you need to add about 1 ml, a lot of starch. It will start to become blue. You can see it's the blue complex is the starch iodide complex's color, and it becomes really dark blue, and you started to titrate it immediately. Okay, this process has to be very fast, because you shouldn't allow the solution to come in contact with the air very long time. So you have to prepare everything before you start the titration. As you're doing the titration, you add the starch and complete it fast. Okay, so as soon as you start at the starch, you complete your titration by adding drop by drop thiosulfate. And you can see the color is getting fed. It will give you a very sharp endpoint. You can see with 1 drop, it will be colorless. Okay, so you are done with your experiment. And then you have taken the volume data from the burette already, the lower meniscus square for the thiosulfate and the final reading. And I'll give you these data later. Okay, আমি তোমাদেরকে আরেকটা হচ্ছে এই স্লাইডে দিয়ে দিব, যেখানে হচ্ছে ডাটাগুলো দিয়ে দিব, এবং তোমাদেরকে সেই ক্যালকুলেশনটা করতে হবে। ক্যালকুলেশন কিভাবে করতে হবে সব এরপরে দেখানো আছে। Okay, from the stoichiometric equation, you can see that 1 mole of oxygen reacts with 2 mole of MnOOH2 and forms 2 moles of iodine. Okay, and 2 moles of iodine reacts, 1 mole of iodine reacts with 2 mole of thiosulfate, right? So 2 moles of iodine will react with 4 moles of thiosulfate. That means 1 mole of oxygen is equivalent to 4 mole of thiosulfate. So we can say that 4 moles of thiosulfate is equivalent to 1 mole of dissolved oxygen. And from that, if you know the concentration of the thiosulfate, so this is like if you know that if you have made 1 normal sodium thiosulfate solution, how you find that equivalent weight? You need to know how many electrons R, each thiosulfate gives, it's a reducing agent, right? So it will give its electron and become oxidized. So the number of electrons is given, donated. You have to divide that. You have to use that divide that formula weight to find out the equivalent weight. Okay, so then as a reducing agent. So you find that equivalent weight and you find out its normality, and that's from that you can find that 1 milliliter of 1 normal sodium thiosulfate is equivalent to 8 milligram of dissolved oxygen. Okay, it's coming from these this relation. Okay, from this. If you convert them into their formula weight, you will find that. Okay. So, and also like oxygen, how many electron oxygen takes? 2 electrons, right? Per oxygen takes 2 electrons, 1 oxygen to become. So 1 oxygen takes 2 electrons, so the oxygen molecule will take 4 electrons. Am I right? So to find the equivalent weight, you have to divide the oxygen's formula weight by 4. So from that, you will find this relationship. You can try to find out this. বুঝতে পেরেছো? এখানে তো দিয়ে দিয়েছি আমি ক্যালকুলেশন করে, তাই না? তুমি এটা বেরও করতে পারো এভাবে, এই যে ইকুইভ্যালেন্ট ওয়েটগুলো বের করে করে। ওকে, আচ্ছা। So using that, you know already the concentration of the thiosulfate, you know the volume from your burette reading, you can find out the amount of the oxygen, and you have done it. Okay, so you have done it maybe for like how many milliliter, say for 100 milliliter of the sample, you have to convert it for the liter. Okay, so that's why it's shown in the liter. Okay, so I'll give you this information, how many, about the volumes, where to put what, and you can do the calculations, you can find the result. Now these are we typically give you 2 different kind of solution sample, tap water and pond water. You have to find out them. So I'll give you 2 set of data later, so that you can calculate on them. And then discussion ki etate to hocche natural sample. You cannot just tell by this like if you are getting the actual result or not. Another method is like if you can compare that with some instrumental method, you can say that how good was your titration was. Okay, that's it. And I'll show you, before we talk about more about discussion, I'll show you a video. Let's see a video. দেখা যাচ্ছে ভিডিওটা? মানে স্ক্রিনটা দেখা যাচ্ছে তো, তাই না?
জি
হ্যাঁ
ম্যাম।
ম্যাম, স্ক্রিনটা দেখা যাচ্ছে।
আচ্ছা, ঠিক আছে, let's see. Can you hear sound? Sound শোনা যাচ্ছে?
সাউন্ড
So first he is rinsing the bottle with the sample water. So you are submerging the total bottle inside and let it fill out and remove all the air bubble. Now you'll put the stopper on it. আচ্ছা, এখানে দেখলে যখন স্টপার লাগালো তখন কিন্তু কিছু পানি পড়ে গেল। এটা ঠিক আছে, কারণ তার মানে হচ্ছে এখানে কোনো এয়ার বাবল ঢুকতে পারবে না। এবার স্টপার খুলে ফেলো। So now you are going to add 1 ml or 1 cc of manganese sulfate solution এবং দেখো যে এটা টিপটা সারফেসের ভিতরে ঢুকিয়ে তারপরে হচ্ছে তোমার অ্যাড করা হচ্ছে যাতে কোনো এয়ার বাবল না ঢুকে and it's colorless you can see pink color. Now they are going to add the alkaline potassium iodide. So sodium hydroxide and potassium iodide is same with the same bottle. So what you are seeing is the precipitate forming and it's sinking down in the bottom. You can see. Okay, if you have like very nice clean solution, then you'll see that this brown precipitate, no solution is brown. See, the solution is still colorless in the top. Only the brown precipitate you can see in the bottom. This is only because of the color of the MnOH3. That color is light brown, and MnOH2, that's MnOH2 is white, but MnOH3, where the manganese is +3, or you can have MnO2, that's slightly brown. So that will give you the brown color, okay? So you mix it so that all the reaction is done. All the dissolved oxygen can make that MnOH3. Now you wait till the precipitate settles. So you will add the sulfuric acid same way down below the surface of the water. And you can see immediately some areas becoming clearing. That means dissolving the water, dissolving the precipitate. তার মানে কখনো যদি হচ্ছে এমন হয় যে প্রিসিপিটেট ডিসলভ হচ্ছে না তখন তুমি আরেকটু সালফিউরিক অ্যাসিড এখানে অ্যাড করবে So you can see the iodine is liberated here and I3 minus is formed here. টাইট্রেশন কিভাবে করতে হয় মনে আছে তো? কিভাবে কোন দিকে ধরতে হয়? যারা রাইট হ্যান্ডার তারা এভাবে হচ্ছে ধরে হ্যান্ডেল করে এবং কোনো বাবল থাকতে পারবে না পুরেতে। আশা করি এই সমস্ত নিয়ম তোমাদের মনে আছে। So you can see they also kept the bottle here so that you can see the color change from this brown to this light yellow color. Note one more thing, they are always keeping this stopper closed of the bottle because you have to do multiple times, repeat this experiment so that you can get an average DU amount from your sample. You know, we haven't added azide, so you can have little bit difficulty getting the endpoint. And it's given in your manuals also. Okay. Okay, it doesn't show that. Okay, so do you need to see it again or it's done? Are you there?
Yes, ma'am, বোঝা গেছে।
Now, if you keep that bottle, the stopper, not closed, okay, but open, what will happen is that with the time you'll see ওখানে যেমন একটা light একটা brown color ছিল না? If you keep that stopper open for some time, you will find that that solution become darker and darker because it can now take the oxygen from the air and can liberate more iodine. So in your discussion, you have to make sure that these precautions are taken, that you are not adding error by making it accessible to the oxygen from the air. You have to always keep the stopper open. Stopper closed, not open. And when you are adding the solutions, make sure that you are adding them below the surface of the water so that you don't have any air coming with your solutions. And give it time to settle down the precipitate when it formed that brown precipitate before you are adding the sulfuric acid. Okay? And also the sulfuric acid has to be added close to the precipitate, that means down in the bottom. So these are some precautions you should take. And one more thing is these chemicals are toxic and irritant. So very careful when you are dealing with these chemicals. So do you have any question?
Yes, ma'am. ম্যাম আপনি যখন আমাদের 1-1 এ ক্লাস নিতেন তো তখন হচ্ছে আমাদের ট্রাইআয়োডাইড আর আয়োডিনের মানে ওয়াটারের সলিবিলিটিটা নার্নেস্টের থিওরাম আর এরকম কিছু হচ্ছে এক্সপ্লেইন করছিলেন ম্যাম, ওটা একটু রিপিট করলে একটু বেটার হতো। ইয়েস ম্যাম, নার্নস্ট ইকুয়েশন দিয়ে একটা এক্সপ্লেনেশন দিয়েছিলেন যতদূর আমার খেয়াল আছে, যদি আমি ভুল না হই ওটা ম্যাম যদি
ট্রাইআয়োডাইডের ব্যাপারে খুব সম্ভবত না, আমি ওটা বলছিলাম হচ্ছে
তখন ম্যাম ক্লাসে মিস করে গিয়েছিলাম, তো ওটা একটু বললে এটা।
আচ্ছা, ওটা বলেছিলাম যে হচ্ছে নার্নস্ট ইকুয়েশন দিয়ে তোমরা হচ্ছে যে কোনো ইয়েকে কি বলে, ধরো ফর এক্সাম্পল লাইক আয়রন, হ্যাঁ, আয়রন 2 থেকে আয়রন 3+ তৈরি হচ্ছে, রাইট? সো ইফ ইউ ক্যান remove the iron 3+ from the reaction, that reaction can move in the forward direction. কারণ কি হয়, একটা স্টেজে এসে তোমার হচ্ছে এই ধরনের রিঅ্যাকশন গুলো, এটা তোমার আয়োডিনের ক্ষেত্রে না, তোমার হচ্ছে আয়রনের ক্ষেত্রে আমি বলেছিলাম, হ্যাঁ যাই হোক আর কি, আয়রনের ক্ষেত্রে তোমার হচ্ছে আয়রন 2 আর আয়রন 3 এটা একটা যদি ইকুইলিব্রিয়ামে আসার সম্ভাবনা থাকে, স্পেশালি যখন রিঅ্যাকশনটা শেষের দিকে চলে আসতেছে, হ্যাঁ। আর ওর সাথে ছিল হচ্ছে যে কি বলে তোমার ডাইফিনাইল অ্যামিন, এই টাইপের ইন্ডিকেটর ছিল, যাই ছিল। তো ওই রিঅ্যাকশনটা যখন তোমার হচ্ছে যে রিঅ্যাকশন কোশেন্ট, যেটা অর্থাৎ তোমার হচ্ছে নার্নস্ট ইকুয়েশনে কি থাকে, তোমার হচ্ছে যে একটা হচ্ছে যে তোমার ইকুইলিব্রিয়াম ইয়ে থাকে না, এক্সপ্রেশন থাকে না, যে কনসেন্ট্রেশন অফ দ্য প্রোডাক্ট বাই কনসেন্ট্রেশন অফ রিঅ্যাক্টেন্ট, এটা ডিফারেন্সটা যত বেশি থাকবে, অর্থাৎ তোমার প্রোডাক্টের কনসেন্ট্রেশন যত কম হবে, রিঅ্যাকশনটা তত হচ্ছে ডান দিকে তোমার শিফট হবে। কিন্তু ইকুইলিব্রিয়ামের কাছে এসে কি হয়ে যায়, তোমার 2+ আয়রন 2+ এর পরিমাণও খুব কম এবং তখন আয়রন 3+ এর পরিমাণ বেশি। যদিও আয়রন 3+ আমরা হচ্ছে ইয়ের থেকে কি বলে হচ্ছে তোমার সলিউশন থেকে আরো অন্যভাবে সরাতে পারি লাস্ট পর্যায়ে এসে, সেটা হচ্ছে যদি ফসফেট অ্যাড করি, ফসফরিক অ্যাসিড অ্যাড করি। সো আয়রন ফসফেট যেটা তৈরি হয় সেটা হচ্ছে তোমার এত বেশি তোমার স্ট্রং কমপ্লেক্স যে আয়রন 3+ কে তোমার ফ্রি আয়ন হিসাবে 3+ আয়ন হিসাবে তোমার ইয়েতে আসতে দেয় না, কি বলে সলিউশনে আসতে দেয় না, ফলে এন্ড পয়েন্ট শার্প হয়। আর ট্রাইআয়োডাইডের ব্যাপারে বা আয়োডিনের ব্যাপারে সিমিলার থিং, এখানে হচ্ছে তোমার এটা হচ্ছে অবশ্যই রিডক্স রিঅ্যাকশন না, কিন্তু এন্ড পয়েন্টের কাছে এসে তোমার যে কমপ্লেক্স তৈরি হচ্ছে, ঠিক আছে, এই যে ট্রাইআয়োডাইড এবং স্টার্চ কমপ্লেক্স যেটা তৈরি হচ্ছে, সেটা তোমার হচ্ছে তোমার সলিউশনে যদি তোমার আয়োডিনের পরিমাণ কিংবা ট্রাইআয়োডাইডের পরিমাণ বেশি থাকে, তাহলে কি হবে, তাহলে যে প্রোডাক্ট যেটা তোমার হচ্ছে আয়োডিন এবং কি বলে কমপ্লেক্স, সেটা বেশি তৈরি করতে যাবে, তাই না? কারণ হচ্ছে ওদিকে হচ্ছে সেটা কমে যাচ্ছে বাম দিকে, অর্থাৎ তোমার কমপ্লেক্সেশন বেশি হবে। কমপ্লেক্স যদি বেশি হয় তাহলে কি হচ্ছে, তোমার আয়োডিন তোমার হচ্ছে থায়োসালফেটের সাথে রিঅ্যাকশন করতে পারবে না। আমার তো দরকার আয়োডিনকে থায়োসালফেটের সাথে রিঅ্যাকশন করে রিঅ্যাকশনটা কমপ্লিট করে ফেলার। সো এই জন্য হচ্ছে আমরা চেষ্টা করি হচ্ছে যে যখন হচ্ছে আয়োডিনের পরিমাণ কম তখন হচ্ছে স্টার্চ অ্যাড করতে, যাতে হচ্ছে সবসময় হচ্ছে যে তোমার কনসেন্ট্রেশন যখনই হচ্ছে আয়োডিনের ইয়েতে সলিউশনে কমে যাচ্ছে, তোমার হচ্ছে স্টার্চের ভিতরে যে কমপ্লেক্স তৈরি হয়েছিল সেখান থেকে আয়োডিনটা বের হয়ে আসতে পারে। বোঝা যাচ্ছে? এই জন্য হচ্ছে আমি ওইটা দিয়েছিলাম বা কম্পারিজন দিয়েছিলাম। অ্যাকচুয়ালি আয়োডিনের ক্ষেত্রে কোনো রেডক্স, এখানে হচ্ছে তোমার রেডক্স রিঅ্যাকশনটা হচ্ছে থায়োসালফেটের সাথে, স্টার্চের সাথে না। হ্যাঁ, কিন্তু কমপ্লেক্সেশন হচ্ছে অনেকটা রিঅ্যাকশন তোমার একই ধরনের তোমার পরিণতির দিকে যাচ্ছে, সেটা বলা হয়েছে। এবার বোঝা গেছে?
ইয়েস ম্যাম। আর আমরা এই থিওরিটা কি ম্যাম যে কোনো উভমুখী রিঅ্যাকশনের ক্ষেত্রে ইউজ করতে পারবো?
অবশ্যই, এটা লাশাটের প্রিন্সিপাল উপর বেস করে, তাই না? ইফ ইউ
জি ম্যাম।
remove the
ইয়েস
product you can drive the reaction to the forward.
ইয়েস ম্যাম। ইয়েস ম্যাম। থ্যাংক ইউ ম্যাম।
Well, আচ্ছা, আর কারো কোনো কিছু? কাউসার, তুমি কিছু বলবে?
না ম্যাডাম, আপনি তো মানে অনেকক্ষণ অনেক কিছু এক্সপ্লেন করলেন, এত ইনফরমেটিভ এবং ইউজফুল জিনিস আসলে। হ্যাঁ, অনেক কিছুই এখান থেকে মানে অনেক ইনফরমেশন আসলে। ওরা লাকি যে আমরা লাকি যে এত সুন্দর একটা ইনফরমেটিভ লেকচার আসলে আসছে আর কি।
আসলে কি এবার হচ্ছে যে ওদের স্যাটিসফ্যাক্টরি ডিসস্যাটিসফ্যাক্টরি এই ধরনের একটা সিচুয়েশন হতে, যেমন যে ওদেরও খুব একটা মানে হচ্ছে যে তোমার ওই পরীক্ষা পাস নিয়ে তেমন একটা চিন্তা নাই, তাই না? সো আমরা হচ্ছে মোটামুটি অনেক কিছু পড়াতে পারছি, কারণ আগে তো ওটা চিন্তা করতে হতো যে এগুলো পড়াচ্ছি ওরা বা চিন্তা করছে। হ্যাঁ হ্যাঁ, যে চিন্তা করে পরীক্ষায় আসবে, এত কিছু পড়তে পারবে কিনা সেটা একটা ব্যাপার ছিল। কিন্তু এখন ক্লাসগুলোকে আমরা আসলে অনেক বেশি ইনফরমেটিভ করতে পারছি এই জন্য। তোমরা কি মনে করো? এগুলো তো আমাদের পক্ষ থেকে আমরা বললাম, তোমাদের কি মনে হচ্ছে? তোমরা কিছু বলো।
ম্যাডাম, আমরা করতে পারছি না হাতে কলমে, এটা আমরা খুব মিস করছি।
হ্যাঁ, এটা একটা সমস্যা। কিন্তু ইনশাআল্লাহ আমাদের, তোমরা তো কেমিক্যালের কাজে তোমাদের আরো সময় পাবা, ঠিক আছে? তোমাদের আরো বেশ কয়েকটা এক্সপেরিমেন্ট করতে হবে, আরো বেশ কয়েকটা ল্যাব কোর্স নিতে হবে কেমিস্ট্রি থেকে, তাই না? সো you'll be able to do some of them and some of them will be repeated but in a different manner. কিছু কিছু জিনিস তোমরা এখন যেগুলো হচ্ছে টাইট্রিমেট্রিক মেথডে করেছো, একই জিনিস তোমরা হচ্ছে 352 তে গিয়ে হচ্ছে ইনস্ট্রুমেন্টের মাধ্যমে করবে। ওই যেমন কালারিমেট্রি অর্থাৎ ইউরিভিজ কিংবা এই ধরনের জিনিস, একই ধরনের ডিটারমিনেশন, আয়রন ডিটারমিনেশন কিংবা নিকেল ডিটারমিনেশন, গ্র্যাভিমেট্রি, তারপরে পটেনশিওমেট্রি, এইসব বিভিন্ন ইয়েতে ইলেকট্রোকেমিস্ট্রি এগুলো দিয়ে করবে, ঠিক আছে? বেটার ইনস্ট্রুমেন্ট আর কি, দামি ইনস্ট্রুমেন্ট দিয়ে করবে তখন। কিন্তু এগুলো হচ্ছে তোমাদের বেসিক তৈরি করবে, তাই না কাউসার?
জি ম্যাডাম, এগুলা এখন তাদের তো আরো কোর্স আছে, এই যে 236 আরো অনেকগুলা। আর তোমাদের আসলে কেমিস্ট্রি শেখার অনেকগুলা সুযোগ আছে, এখান থেকে কেমিস্ট্রিটা আসলে তোমাদের অনেক ভালো লাগার কথা আর কি। মানে যদি বুঝতে পারো যে আসলে কি সুন্দর এখানে অ্যানালাইসিস করা যাইতেছে আর কি সুন্দর এক্সপ্লেনেশন। হ্যাঁ, এটা খুব মজার জিনিস আর কি। এবং এই জিনিসগুলো এই যে ডিজলভ অক্সিজেন খুবই প্র্যাকটিক্যাল। হ্যাঁ, খুবই প্র্যাকটিক্যাল জিনিস। এক্সপেরিমেন্ট গুলা যে দেওয়া হয়েছে মানে ডিজাইন করা হয়েছে তোমাদের কোর্সের জন্য, খুবই প্র্যাকটিক্যাল। হ্যাঁ, এগুলা একবারেই অ্যাপ্লিকেশন বেস রিলেটেড।
আর যদিও আমরা এখন সবকিছু যে ইনস্ট্রুমেন্ট বেস করি, কিন্তু তারপরে মাঝে মাঝে এমন সিচুয়েশন তৈরি হয়ে যায়, যেমন ধরো এই যে ইয়ার কথাই বলি যে হাওড়ের যে সিচুয়েশনটা যখন চলতেছিল, এই সময় আমাদের যে ইনস্ট্রুমেন্টগুলো, আমাদের ডিপার্টমেন্ট প্লাস তোমাদের ডিপার্টমেন্টেও ইনস্ট্রুমেন্ট আছে যেগুলোতে বিভিন্ন ফসফেট এগুলো অ্যানালাইসিস করা যায়, কিন্তু সামহাও ওই মুহূর্তে আমাদের ডিপার্টমেন্টেও এবং তোমাদের ডিপার্টমেন্টেও কোনো ইনস্ট্রুমেন্টই ফসফেট ইয়ে করতে পারছিল না, রিয়েজেন্ট ছিল না। সো তখন আমাদের এই ধরনের টাইট্রিমেট্রিক ওয়েতে বের করতে হয়েছে যে নিউট্রিয়েন্টের পরিমাণ কি পরিমাণ ছিল হাওড়ের পানিতে, ঠিক আছে? সো কেননা ওগুলো হচ্ছে তোমার টাইম, মানে খুবই টাইম ডিপেন্ডেন্ট তোমার এই এক্সপেরিমেন্টগুলো। তুমি যখনই স্যাম্পলটা কালেক্ট করবে, তুমি যদি স্যাম্পলটাকে যদি হচ্ছে ফ্রোজেন অবস্থায় রাখো, ফ্রোজেন ঠিক না, মানে কুল অবস্থায় রাখো 2 থেকে 4 ডিগ্রি সেলসিয়াসে, তাহলে তুমি 8 ঘন্টা পর্যন্ত রাখতে পারবে অ্যানালাইসিস করার আগ পর্যন্ত। কিন্তু অবশ্যই 8 ঘন্টার মধ্যে তোমাকে অ্যানালাইসিস করতে হবে। এই যে এক্সপেরিমেন্টটা করলে এটা 8 ঘন্টার মধ্যে করতে হবে, বা অন্য কোনো মেথডে যদি করো ইনস্ট্রুমেন্টে দিয়ে 8 ঘন্টার মধ্যে এক্সপেরিমেন্টগুলো করতে হয়। সো বুঝতে পারছো যে ওই মুহূর্তে যদি তোমার জানা থাকে, তোমার ইনস্ট্রুমেন্টে কোনো সমস্যা থাকে, কিন্তু তোমার যদি এই টেকনিকগুলো জানা থাকে, তুমি ইমিডিয়েটলি ওইটা করে ফেলতে পারছো, তোমাকে আর ওয়েট করতে হচ্ছে না, মানে তোমার স্যাম্পল নষ্ট হচ্ছে না। বোঝা গেছে কেন এই জিনিসগুলো শেখানো হয়? ওকে,
ইয়েস ম্যাম।
আচ্ছা, তাহলে আর কোনো কোশ্চেন?
ম্যাম, রিপোর্টে কি আমরা সি আর ই পার্টটা অ্যাড করব নাকি ওই দুইটা বাদ দিব?
ওই দুটো আলাদা, ঠিক আছে? প্রথম রিপোর্ট সেটাতে তোমরা হচ্ছে ওই হার্ডনেসেরটা ও ও যেগুলো আমরা এখানে আলোচনা করি নাই, না ওগুলো বাদ দিবা, দরকার নেই।
আচ্ছা ম্যাম,
ঠিক আছে, ডিসকাস করা হয় না, সেটা রিপোর্ট লেখা দরকার নেই। আর আমি ডেটা দিব হচ্ছে এটার উপরে। কাউসার কিছু বলবে?
না ম্যাডাম, ঠিকই আছে, সব তো বলা হয়েছে। তো তাদের যদি আর কিছু কোশ্চেন না থাকে তাহলে তো আমরা শেষ করতে পারি মনে হয়।
হ্যাঁ, আমাদেরও সময় শেষ, আজকে একদম অনেক বেশি সময় লেগে গেছে।
অনেক কিছু বলছেন তো ম্যাডাম, অনেক কিছু। জি।
আচ্ছা ঠিক আছে, তাহলে আল্লাহ হাফেজ।
হ্যাঁ,
আসসালামু আলাইকুম ম্যাম।
ওয়ালাইকুম আসসালাম।